Hi friends, welcome to my loft classroom. So I'm going to do a short lesson today about work and power and simple machines, and then you guys are going to get to put some of that into practice in the classroom, and it's going to be a really great day. So last week we learned about work, and we did a lab where we were experimenting with the difference of how much power our hands had and maybe how much power our legs had as we were going up the stairs and as we were rolling up the spaghetti boxes on it. And so we worked through a lot of those examples and those equations, and you did that for your lab this week. So we're going to tie it all together and see how does that get used in everyday life. Well, first, when we talk about work, quick reminder, work means motion has to happen. So if you tell your boss, I'm doing work, but nothing has actually happened, they're going to say, what work did you do? So, and if you were maybe asked to take the trash out to the street, and you went and you stood by the trash can, you opened the trash can, but you actually didn't take it to the street. You didn't do the work of moving the trash can from one place to the street. So work is important because it is a force applied over a distance. So remember, we have to have a distance moved for work to actually happen. And then what's neat is once we know that work, we can then decide how fast did we actually move it. Were we going up the stairs, or are we pushing the trash out at our slowest possible pace? Well, then the power that we're putting in there wasn't as much. So power, we remember, is our work divided by time. It's work over time. And so as we get to know all of these parts, remember we were first learning force. Then we got to apply force over a distance, gives us work. Work over time gives us power. So it's always important to be able to go back and know, where did we start? What are maybe all the forces at play? And how does that affect the total power of a system for it? So if work is force over a distance, are there different options? I think we've seen that. We've seen static friction, kinetic friction. We've seen static energy and kinetic energy. So we're always kind of having these two different sides of it. Well, when it comes to work, we have our input work and we have our output work. And that really seems to go right along with our Newton's laws that every action has an equal and opposite reaction. And so if we're inputting something into a system, it's going to be outputting maybe back on us or back onto something else. It has to push somewhere. That was the Newton's law. Every force, and then also we've got energy. Energy is neither created or destroyed. All of those have to continue to be true. And so as we're inputting something into a system, it has to output somewhere. We've got to have that equilibrium, that balance for it. So let's look at work that is our input work. When we are inputting work into a system, it is the amount of force. Remember, work is always force times distance. So the amount of force times the distance that we apply it. So we're going to have force applied over a distance, and it's all the parts that are going in. The thing that's important to note about this is, since work, say we have our work input and we have force times distance, the force of input and distance of input, this is a direct relationship. And we talked a little bit about that. So if our force increases, then our work must increase. If our force stays the same and our distance decreases, then our work must decrease. These are direct relationships. They're on opposite sides of the equal sign, and they are both in the numerator of your equation. So they are a direct relationship. Now, if we address force and distance together and we want our work to remain the same, if this is an inverse relationship. If force goes up and I want the same amount of work, then my distance has to go down. So we can decide how much we're putting into a system. We can decide how far we need to go, how hard we need to push based upon this equation here of knowing it requires so much work, and so I need to apply, I either need to get stronger or I need to make it go a longer distance. Something that is really important to me about this whole process and about our simple machines that we're going to get to in just a minute is the fact that my dad's a paraplegic. I've told you guys that before, and so he's in a wheelchair. So when you're having to push somebody or he's having to push himself in different places, he can either push his wheels harder, or he to have the same thing, or he can have a longer distance maybe to travel for that. And so it's interesting whenever we were building a ramp onto the front of our house that these things mattered. And so this is everyday life for lots of engineers, for builders, architects, carpenters. Many jobs use this, and I'm going to show some examples later. Okay, so if we have that input system, we have to have that output system. Remember, we've got those two parts. So again, because it's work, it has to be force times distance. We can't change the formula of it. So the output is now the force that is outputted on the system times the distance of the output exertion, the distance of which that output is played out over. So when we compare these, we come up with two different formulas. And what I want you to notice is that they're actually comparing different parts of the work equation. So mechanical advantage, we talk about mechanical advantage. I have a fantastic video from Mark Rober. Who doesn't love Mark Rober? For you guys on mechanical advantage, and it is on the Google Classroom, and I really, really want you to watch it. So promise me that you'll do that. But a mechanical advantage, what is it if you have an advantage? Like you're one up on the person, right? Or you're getting a head start, or it's to your benefit. So if you want something to be to your benefit, you want more benefit, right? So when we have our mechanical advantage, the higher our number is, the more benefit it is to us, the better it is for us, maybe the better it is for the system. So as we're working through and you're looking at the different numbers that are playing out, the higher the mechanical advantage, it means it's helped you out a whole lot more. And you're getting more work than you put in to that. So when we have our mechanical advantage, again, we're back to two sides. We have actual mechanical advantage, and we have ideal mechanical advantage. And that's something that we deal with a lot in life. There's actually what you have in your bank at your house, and there's your ideal of what you should have. That really works out when you're an adult. There's an ideal amount that is a salary that you say you are given by your employer, and then there's the actual amount of your salary after they take out taxes, after they've taken out health insurance, after you've paid, into the company stock, whatever that looks like. So we've got this ideal, meaning if we were in a void, there's nothing else affecting the system, we would have our ideal system. But then there's the actual, like this is real life. There's other things at play all the time. So when we talk about our actual mechanical advantage, it is going to address force. And the way that I remember to keep those two things together, actual means there's probably going to be a problem in that system. Just like the actual take-home pay that I have means I've got some taxes in my system. Okay? And force, when we look at the difference between force and distance, which one of those could have some problems in the system? Distance is a scalar number. It's measured. It's pretty concrete. Distance is going to be the same on Mars as it is on Earth or in space or in a mine shaft. It's kind of all going to be the same. However, force has problems in the system. That major problem is friction. So remember, as we applied force, our total force, that goes all the way back to our previous models, our total force is our applied force minus all of our frictional forces. So we know that when we are looking at force, we've got some things that are being drawn out of that system. So actual mechanical advantage deals with the forces, the output force over the input force. And so if I can put in, maybe push down 5 pounds onto a lever, and I can lift 50 pounds on the other side of that lever, then I would have an actual force of 50 pounds is what I lifted, but I only pushed down 5 pounds. So my actual mechanical advantage would be 10 in that case, and that's pretty good. If I could change that system and I could have a 500 pound item and I could still push down just with 5 pounds, then my actual mechanical advantage is 100. A lot better. The thing that's going to have to change would be those distances. Remember, these are direct relationships. Okay? Now, when we deal with ideal mechanical advantage, we're not dealing with force. Ideal means perfect system. There's nothing that's ever going to be drawn out of the system or cause that system to change. So ideal mechanical advantage deals with the distance portion of our work. And so if you notice, these are flip-flopped. You might say, well, actual is my output over my input. So shouldn't ideal be output over the input? It's not, because ideal is how much are you actually having to work and push down in a system. And remember, when we have work and we've got force over distance, I want to be really lazy. Let's think about that way. I really don't want to push very hard on this. So I want my force to be this very tiny amount here. But I want the work to be the same. So when my force, or let's say, let me push this down. So when I have a lower force and I want to get the same amount of work out of the system, I have to increase my distance. So I'm going to have a little bit of amount of force, because in our actual system, our actual mechanical advantage, we want this denominator to be as small as possible. The smaller this number is, the higher my mechanical advantage is. And that's the goal. We want this to be as bigger than 1 as possible. And just like fractions, if I have 1 pizza and I have to divide it among all of you in class, we're all getting tiny pieces. But if I just have 1 pizza and I decide that I'm not going to share with any of you, or maybe me and Miss Thompson are going to be the only ones that are going to eat the pizza, we get bigger pieces. It's better for us. So the fewer amount of pieces that you need to divide it, that smaller amount of that denominator, smaller input force. So if we're looking at work, I want a tiny force. That means I have to have a large distance. And we want the biggest number on top. So when we go to ideal mechanical advantage, that's talking about our distance, we want this really big number on top because we want the tiny number on the bottom. And so we have our input distance over our output distance. So we might have to input force over a longer distance, but that means that our output might be really short, and that's what's going to be addressed whenever you guys do your fulcrum experiment today at the end of class. So that's how work works together. And when we can see that these are inverse properties or direct relationships and that they really all tie together, hopefully you can see it's not just here's some new numbers that are thrown at you, but it can make sense of which ones you want. We want these numbers on the top to be our biggest numbers. We want the numbers on the bottom to be our tiniest numbers because we want that mechanical advantage to be to our benefit, to the best of our ability. Okay? So in your book, it had talked about some ramps, and I talked a little bit about ramps that we had to build for my dad. So when we are looking at ramps, and it said you have a ramp, and it is, let's see, 2.74. I'm going to work the one in the book. 2.47 meters long. Okay. And it's lifting 0.91 meters up. Okay. Since they have given us a distance, we know that we are working with ideal. Distance has to work with the ideal mechanical advantage. Okay. So we've got our ideal mechanical advantage, and when we've got ideal, we want our distance, our biggest distance, to be on top. And so that's going to be our input distance. So we have 2.74, and how do you know what is your input distance? That's the part where you're starting. Where do you start and where do you have to input to end up where you're going? So when you're looking at a ramp, let's see if we can talk through this. You're wanting to get up here to this platform. You could start and take a big step up or a big jump up, depending upon how high it is. But your final movement is the distance, is the direct vertical distance that you need to travel. I need to go from 0 to 0.91. So that would be my output. Instead, I'm going to start over here on the left, and I'm going to start inputting steps. And I'm going to keep inputting steps, so I am actually doing something. I am inputting work into the system, inputting effort over a distance of 2.74 meters. So our input distance is 2.74. Our output distance is 0.91. We're going to divide those numbers, and we get 3. This 3 means that it was 3 times easier, to my advantage, 3 times easier for me to push that box up or carry whatever I had, for me to go over the ramp than it was if I stood right below it and I tried to heft it maybe up on to the moving truck or something. So that was a good one. Now, what would happen if that still hurt my back? I could take my ramp, let's do this. I could take my ramp and I can make my ramp longer. So what if I was now not going 2.74, but I was going 5.48 meters? I made my ramp twice as long. Now when we divide, my mechanical advantage should be 6. Now it's 6 times easier for me to take whatever I'm taking. I'm having to walk a lot further, but maybe it's not going to throw my back out this time. Okay, so that's how our work and our mechanical advantage plays out. Okay, so then your book talks about efficiency, because every system is not perfect, and especially since this work depends on force and distance, and we know that force always has some things that are drawn out of that system, specifically friction. So if we're looking at efficiency, we're never going to get the same amount of work out of a system as we were able to put in to the system, because something is going to be grinding, or we're going to have some friction, or there's going to be some heat that is released, so we don't have all the same energy there. So efficiency is basically just saying, in a perfect world, it'd be 100%. But we want our efficiency to be as high as possible. And so our efficiency is always, how much did we actually get out? So our output divided by how much work we put into it. Okay? And we want our efficiency, that will give us a decimal, and so we can get it, we can turn it into a percent by multiplying times 100, or we can just use our percent sign on that. So how much did we get out divided by how much we put in? And we are never ever going to get more out of a system than we actually put in, which means our number on the bottom is always going to be greater than our number on the top. Okay? And so when our number on the bottom is bigger, so if our number on the top was 8, our number on the bottom has to be bigger. When our number on the bottom is bigger, we will always be less than the number 1. And that's why it's going to be a percent. It will never be more than 100%. If you ever get like 1.2 something, flip the numbers. You've got them in the wrong order. It should always be less than the number 1. Okay? So now, simple machines. I'm going to go over a couple of things, and then Miss Thompson is going to take over and let you guys play and experiment and do a couple of labs and get some hands-on, which is going to be great. So, simple machines are great. There are 6 main simple machines. They have them in your book. I have them on the slides. If you look at the slides, there's a simple machine scavenger hunt on there, which is super fun to think about simple machines that are found in everyday life for it. But we have our incline plane. We already talked about that with the ramp. There's a wedge. If you've ever split wood, a wedge is used to drive down between something and make it separate out. There's the pulley system. And I have a little example of a pulley system. So pulleys can operate in different ways. When you have a basic pulley like this, the mechanical advantage is 1. And so then you might ask me, Miss Thomas, why would you even use a simple machine if the mechanical advantage is 1? That means it's not giving you any extra advantage. It's the same amount of work as it was if you just picked it straight up. Well, what's different about a pulley is it changes the direction of the force. So if I have my bottle, I have to apply full force to lift it straight up. That means my bottle is working against gravity and my arm is also working against gravity. However, if I use a pulley, I am now pulling down and working with gravity. So only the bottle is working against gravity and I get to work with gravity. And so it takes away a little bit of that extra effort that I'm having to put in there. Now, for pulleys, you can double pulleys up. We could attach a pulley directly to the bottle and then make a double pulley. So the more lengths of rope that go through the pulley system, each one of those links increases that distance, which means it decreases the force you have to apply to do the same amount of work. So if you have something that's super heavy, you'll see where they wrap up a pulley system maybe 6, 7, 8 times. They'll have, a pulley system put together, and that means they're able to do 8 times more than what they could do with just one. That's a pulley system. There's levers. Levers are great. They're all over. Seesaws are our favorite lever on the playground. So you can have a couple of kids on one and a couple of kids on the other, or maybe one. And when you're little, you just figure it out. You know that if there's someone heavy, they need to scoot a little bit closer to the front, and the lighter people need to scoot a little bit further back. And that's because we are dealing with that distance. We need the same work. They weigh the same. We can't change their weight, during recess. So we have to change the distance for that. Levers, I have a couple of here. I love woodworking, and so I deal with hammers and nails a lot. And unfortunately, sometimes they just get nailed in the wrong place. If I were to try to pull this nail out with my hands, I'm gonna hurt my fingers. However, I can take the end of a hammer with the crowbar part, and what it is doing as I am working with gravity and pushing down, the tip of the hammer, the claw part, is pulling up onto that nail. Another thing that has happened is I increased my distance. So the work happens right here where the hammer met the nail. So when I have my fingers on it, my distance is none, and I'm having to apply tons of force because I have no distance to expand to get that same amount of work. But whenever I put the hammer on that nail and I get to move my hands up, the distance increases, which means my force got to decrease to do the same amount of work. If it's something that's really hard, or you'll see maybe out on a construction site, they will have really, really long crowbars because it is multiplying how their distance there is raising really high, so their work gets to go a lot higher for that. Okay. Another one that's super fun is the screw, and I like this one. This is an old hand screw where you would hold here and you actually get to spin it around like that. And once it gets set, you're gonna hold the top and it's gonna spin around. But if you can see, a screw is really a ramp that is just wrapped around. And there's different screws. So the further apart the threads are on the screw, the more amount of material that it's having to pressure through on that. Because if I were to maybe cut off this ramp and spread it out and actually like lay it all out, you would see that the distance might be maybe 4 times the amount of the top of this. However, I have this wood screw. You can see that the teeth are a lot closer together. So the amount that it's going down is a less amount each time. So our distance again has gone down. However, it's going to require less force than that big one. And then we can go down even to our tiny metal screws, and the threads on it are really close together. And so it's every turn, you're maybe only moving maybe a millimeter for every turn on this one. However, the material that it's going through, if you're going through metal, is not going to have much give or leeway on that. So those are a couple of the simple machines and how we use them in everyday life. Another really great one is the wheel and axle. So one of the fun things is if you try dragging something across the floor, you're gonna have all that friction, right? So we learned that when we dealt with friction, is that we wanted this very smallest amount to touch for the friction. So when we add a wheel and axle, we now have our points where their friction are very minimal. We can overcome that static friction a lot faster, and then we can move forward with our kinetic motion and energy and just kind of deal with that system. So wheel and axles, bicycles, cars, and we're very thankful for the wheel. So that's the end of lecture today. You guys have fun doing hands-on with all of your simple machines and seeing how they can help make your work a whole lot easier.